We tend to think of our modern internet as an invisible, wireless web of cell towers and satellites. But in reality, nearly all human data is carried by physical infrastructure spanning the ocean floor. Beneath our city streets, that data travels through strands of glass no thicker than a human hair. Guiding light through these strands is physically difficult. When light hits a standard pane of glass, it simply passes through it via refraction. If you try to send a signal down a plain glass tube, the light immediately escapes out the side. Engineers solve this by wrapping a dense glass core in a slightly less dense glass layer called cladding. When light hits this boundary at a shallow angle, it doesn't escape, it bounces inward. This creates a continuous zigzag path down the tube through a process called total internal reflection. This mechanism turns glass into an interference-free data pipe. However, maintaining that signal across thousands of miles of ocean required engineers to account for the specific molecular behavior of glass itself. The first obstacle to long-distance transmission is attenuation, or signal loss. At a microscopic level, glass is not perfectly clear. As light moves through the core, it encounters microscopic fluctuations in the density of the glass. When photons hit these imperfections, they scatter in random directions, a phenomenon called Rayleigh scattering. This scattering is highly dependent on wavelength. Shorter wavelengths, like blue light, scatter drastically more than longer ones. To minimize this loss, engineers moved their transmission lasers out of the visible spectrum and into the infrared. By using light at a wavelength of 1550 nanometers, the signal encounters much less resistance, effectively making the glass invisible to the light. By adapting the lasers to the inherent molecular flaws of the glass, engineers reduced signal fade, allowing data to travel significantly further before dying out. Even a bright signal can become unreadable due to dispersion. In early fiber designs, the data pulses would eventually blur into unrecognizable noise. This is caused by modal dispersion. In a wide core, light can take hundreds of different zigzag paths, or modes. Light taking a steep, bouncing path travels a longer distance than light going straight down the middle. Because these rays arrive at different times, a crisp data pulse smears out as it propagates. The solution was to shrink the glass core to a microscopic 8 to 10 microns. This created single-mode fiber, which is so narrow that it only allows light to travel in a single, straight line. By forcing the light into this single-file path, engineers eliminated the Bernardin effect, ensuring that massive volumes of data remain distinct over vast distances. However, even a perfectly crisp infrared laser inside a single-mode fiber eventually loses its energy. After a few hundred kilometers, the signal becomes too weak for a receiver to detect. Early networks used electronic repeaters to catch the light, convert it into electricity to boost it, and then fire a new laser. This physical conversion was an expensive and slow bottleneck. The solution was the erbium-doped fiber amplifier, or EDFA. This device amplifies the signal directly, without ever converting it to electricity. Inside an EDFA, engineers inject erbium ions directly into a section of the glass. A background pump laser is used to keep these ions in an energized state. When a weak data signal enters the section, it triggers the excited ions to release identical photons. The signal is essentially cloned and built back up to full power without ever leaving the glass. The EDFA allowed for optical amplification based purely on physics, removing the final speed limit on how fast data could travel across the globe. Addressing these challenges of loss, blurring, and decay enabled the use of dense wavelength division multiplexing, or DWDM. In a DWDM system, the fiber acts as a multi-lane highway. Instead of one pulse, we send dozens, or even 160, different wavelengths of data down the same microscopic strand at the same time. Maintaining this global system requires instruments like the Optical Time Domain Reflectometer, or OTDR. This tool injects a light pulse and analyzes how it reflects back off the internal structure of the fiber to pinpoint the exact location of microscopic breaks or losses in the glass. This technology is a continuous industrial reality. Factories produce and spool thousands of miles of specialized cable to maintain the world's increasing data demands. Every digital interaction we have today relies on these specific modifications to the behavior of light. What began as a simple observation of reflection in glass has become a global infrastructure that operates at the edge of physical possibility.